Thank you, Asim. So, thank you for good morning, and thank you for joining again today. I see as many people almost as yesterday, so I hope we didn't scare most of the people away. We are, of course, live here on Zoom, here from IUCAA, Pune, and also a live streaming on YouTube. What I've been doing is going through the basics of astronomy and astrophysics in terms of setting the basic principles down of why we are doing what we are doing in astronomy astrophysics, which is what I covered yesterday. And today I'm going to talk about basic measurement in astronomy, starting from the kind of measurement that we naked eye without telescopes talk about, which might be slightly different from how other kind of physicists or scientists make measurements. I mean, there are certain units, certain ways of looking at the universe that is pretty typical of astronomy. And often astronomers forget that the rest of the world don't work that way, don't see the universe that way. And so even though this might seem a little boring for some of you who are familiar with it, I think I'm trying to address the larger part of the audience who have not come across astronomy and astrophysics before. And knowing the basics of measurement in astronomy is going to help in almost all the lectures in this series. And so here we go. The other thing is that what I will do after this, of course, is going to talk about measuring the scale of the universe and how large the universe is and how old the universe is. And these are questions that were also asked yesterday. And these are some of the fundamental things that you have to know in order to understand most of what's covered in this course. And so this lays the grounding for it. So yesterday, I talked about how our basic unit of distance will be a parsec, written as 1 PC, and that's 3¼ light years. People understand light years because they understand that's the time it takes for light to go in a year. That's the distance covered by light in a year. And so, and parsecs is slightly bigger than that. And I'm going to explain a little later why we use parsecs instead of light years, right? And the size of a normal galaxy is maybe 25, 30, 50 kiloparsecs being 1,000 parsecs. And the average distance between galaxies in the universe, and I established yesterday that galaxies are the basic building blocks of the universe. They are the molecules of the universe, as it were. And that's a megaparsec. So 1 million parsecs. And within the galaxies, there are stars, and they are roughly about a parsec away, unless they're in clusters, of course. And then the size of the observable universe is gigaparsecs, right? But actually, an astronomer makes measurements on the sky, not in parsecs or in kilometers or meters, because we don't know the distance to most of what we see in the sky. I look up at the night sky, I see stars, I don't know how far they are. I draw constellations by joining dots, but the dots I join might be at different distances from me in 3D space. They might be totally unconnected. So the most convenient thing for an astronomer to make a measurement is to measure an angular size. So not just size, but distances. So when I say that I find there are 2 stars in the sky, I say they are a degree apart or 3 minutes of arc apart. And apart on the sky does not mean I'm measuring in parsecs, I'm measuring in angles, right? And of course, the relation between linear size and angular size is given here. So that's the main thing. And we astronomers would quote distances and sizes in a different way than most people would do in science. And these we talk in angular sizes and angular distances, and most often they are expressed in radians, which is dimensionless. So the size of the moon as a reference frame, and the size of the moon is half a degree, right? That's also the size of the sun. Size of the full moon, well, of course, varies from day to day, depending on the distance of the moon from the Earth, but varies very little. It's roughly about half degrees. That's the idea. And then the angles are from horizon one side to horizon the other side is 180 degrees, right? So that's how you set the basic the scale. So you can work out various things to see whether how these angular sizes correspond to things you see at a distance, things you, how can you measure these distances? So for example, here is a textbook picture of how to remember how big things are. Once you put your hand outstretched in front of you, a finger is about a degree wide, and the segments of the fingers, as you can see, are 3, 4, and 6 degrees roughly. It, of course, varies from person to person. But so those are, it's very surprising, these results. You never thought of your finger being a degree wide. And that's absolutely true, and it's twice the size of the moon. And your palm would be about 10 degrees, right? So that gives you an idea of when we say something is, so many degrees away from each other, exactly. You could do this without any equipment. You could look in the sky and you can find something with respect to another thing. And this is what people have been doing for a long time. And the earliest texts of astronomy, you will find that people say, so-and-so star or so-and-so, pattern constellation is so many hands away from so-and-so. So this is how we measure, right? And here's a good comparison. The nearest galaxy, the big galaxy we have, is the Andromeda Galaxy. This is not a real picture, of course. This is a superposition of two pictures to show the real sizes, but actually this is to scale. The size of the Andromeda Galaxy on the sky is about 4 degrees, and that's 8 times the size of the moon. This is, of course, if you take a very, very deep picture of using the biggest telescopes, you can actually probably see Andromeda's outskirts go much further out. But the Andromeda Galaxy is so big. Actually, you can see with the naked eye quite a bit of the Andromeda Galaxy if you're in a dark site away from the cities and you haven't been looking at television for a while, so that your eye is settled in darkness. Even from, say, our observatory site 100 kilometers from Pune, or from GMRT, or places where there aren't too many street lights, if you look up at the sky, you can spot Andromeda with the naked eye. You won't see the whole size of the 4 degrees, but you can probably see the central bit. So, so galaxies are much bigger, of course, in real terms, but even the nearest galaxies are huge. If you live in the southern hemisphere, you can see the Magellanic Clouds in the sky, which are the dwarf galaxies that are satellites of the Milky Way, very clearly with the naked eye, and they are much, much larger than that, almost much larger than what we see here for the Andromeda Galaxy. Now, here is something that I would like you to understand before we move on. Now, we say that the angular size of a star is its distance. Its distance determines its angular size, the real size divided by its distance. Now, if you calculate that for most stars, or not most, all stars other than the sun, you will find that the angular size is very, 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 very small compared to even a second of arc, which is 1/3600th of a degree, right? And yet, when you take a picture of stars with a camera, you find that the angular size of stars is probably 2, 3, or 4 degrees, depending on where you're taking. The best sites of the best sites where telescopes are put on the Earth have star sizes in their images of maybe a quarter of a second of arc, right? Now that's the best you can do. With the Hubble Space Telescope, it's even better. Now, why is there a difference between image from the Hubble Space Telescope and image from even the best place on the Earth taken with a telescope? And this is known as seeing. Seeing is the best image that you can get of a point object. And a star, for all intents and purposes, a point object, because its typical angular size would be much, much, much smaller than a second of arc. And you'll see them on an image as a few seconds of arc. And here is a very distracting image, and that is why I put it up, just to illustrate what astronomers are very concerned about when they take images and they figure out how they're doing in terms of measuring sizes, their resolution, and measuring distances between them. And that is that as the light comes through the atmosphere to the astronomer, to the telescope, or to your camera, to your eye, what happens is that it passes through this entire length of the atmosphere to reach you. The atmosphere is maybe 100, 150 kilometers of air, and every layer of the atmosphere has a different density, temperature, and pressure. And as a result, the refractive index, local refractive index of that layer is different. So the light coming from the source, coming through the atmosphere, actually is passing through various different layers that have different refractive index. And so it is refracted in a different way and comes in a zigzag fashion. And each photon then lands on your image, on your photographic plate, your camera focus, etc., at the back of your eye, at a different place. Now, these are very slightly different, but it depends on how turbulent the atmosphere is and how drastically the temperature and pressure structure and the refractive index of the atmosphere is changing about it, right? And as a result, if one takes an image that is an exposure of a few seconds or a few minutes, as we do, I mean, I've taken images that may be even an hour long, then during that time, the photons from the same object would land in different places. Now, this is why stars twinkle. You're talking about twinkle, twinkle, little star. Stars twinkle because even in the 1/10 of a second, or whatever, which is the integration time of my eye, I see the photons from the same star land in a different place within my eye, the detector of my eye. And as a result, I can see the star's position change, right? Now, if you then integrate over this very long period, what you get is a blurred image, an image that is very large, because during that time, the photons from the same star has landed in different places. And this is why we see a blurred image of a star. The star is not what its actual angular size is, which could be 10 to the power -5 arc seconds, but it is actually 1, 2, or 3 arc seconds, and that is called seeing, right? So any image that we take will be the highest resolution of that image will be the seeing of that place, because the telescope or the detector that is using it is taking that image, has to take that image while the light has to pass through the atmosphere. And this is one of the reasons, not the only reason, but one of the reasons we send telescopes above the atmosphere, because above the atmosphere, this effect is not there. So the highest resolution of any optical image taken above the atmosphere with the telescope in space, it could be AstroSat, it could be the Hubble Space Telescope, would be the resolution of the instrument itself and the resolution of the telescope, not the resolution of the instrument and the telescope and this blurring effect of the atmosphere. Okay, so we have to understand that if you want to see two stars that are very close by, then we talk about the distance in terms of angles. We say this is so many minutes of arc or seconds of arc apart from each other. But we also have to understand that we won't be able to see them as distinct objects if they are so close that light from each of them are blurred into the same image due to this effect called seeing. Okay. Now, I'll come back to this issue later on when we talk about real measurements of things to do with distances. But I come back to the issue where I ended yesterday. And we are making a distinction between then the genuinely point objects in the sky, which are the stars, and the fuzzy objects in the sky, which are the galaxies. Now, I told you that the nebulae or the fuzzy objects in the sky are not all galaxies, but many of them are. And the galaxies are the ones, the fuzzy objects that are really far away, that are megaparsecs away, more than millions of parsecs away. And these are islands of stars of their own, and these form the basic building blocks of the universe, right? And normally, nearby galaxies are blurred by the seeing, but that doesn't make it impossible for us to see the structure of the nearby galaxies, as you can see, because they are much bigger than the seeing. The stars themselves, if they had planetary systems around them, or if they had features on the stars themselves, we wouldn't be able to resolve the effects of these stars because they would be blurred by the atmosphere. So these are pictures taken from ground-based telescopes, other than this one, which is a space-based telescope, a Hubble Space Telescope picture. But you can see that there are different kinds of galaxies. The interesting thing about galaxies are, let's talk about the galaxies before we go back to the distance measures again, because it is measuring the distances of galaxies that will give us the size of the universe, as it were, instead of measuring distance of stars, which are within galaxies. There are two different kinds of galaxies, basically. The spiral galaxies, which form about 75% of all galaxies, most of the rest being nice and round elliptical. We now know that elliptical galaxies are older galaxies. Spiral galaxies are galaxies that are younger. They have star formation. But the interesting thing is that galaxies are not, they don't like to live alone. They interact with each other a lot. They like to live in small groups, big clusters, and they are often crashing into each other, merging with each other, interacting with each other. Is a good example of the Stephan's quintet, where actually there are 4 galaxies in which you can see evidence of star streams coming out of one into the other, and they're pulling stars out of each other's other galaxies. So they actually interact, and eventually they merge and form bigger galaxies. And when we come to talk about galaxies in more detail, we'll talk about them. So our galaxy is like one of these, and as I said, it's a galaxy that, this is the slide on which I ended yesterday, and this is the galaxy that we live in, and it's flat, and we don't live in the middle, and we live very near one of these arms. Now these arms are full of these blue patches, and these blue patches are places where stars are forming, and these have molecular clouds in which stars are forming, and this is why spiral galaxies in their disk form stars much more frequently, much more often. This is seen than galaxies that don't have disks and are much older. And some of these spirals or disk galaxies will merge with each other to form rounder galaxies, and the elliptical galaxies are formed out of these spiral galaxies. So we just look. Where I stopped yesterday was when I started telling you about how we see the stars. What we do is we see the sky through the screen of stars that surround us from the galaxy, right? So we look in this direction, and we look in this direction, and we see stars, And then beyond that are the galaxies. So if we have a powerful telescope, we can see beyond the screen of stars out here, right? And if the Andromeda Galaxy is out there, for example, the picture I showed you, we see it through the screen of stars in our own galaxy. And our naked eyes are powerful enough to see the nearest galaxies. But actually you need a telescope to see most galaxies, right? Now, if when we live in the Northern Hemisphere, even from the southern tip of India, the Earth blocks most of this view of the Milky Way. We see the Milky Way, but really you have to go to the Southern Hemisphere to see it in its full glory because it'll be high up in the sky. And this is, for example, a view of the Milky Way from Chile. It's a place where I've been many, many times to observe Cerro Tololo in the northern part of Chile, in the Atacama Desert, on top of the Andes Mountains. One of the best places to observe from. The seeing here is always less than a second of arc. It often goes down to 0.2, 0.3 of a second of arc. And anywhere in the Southern Hemisphere, particularly from very nice and dark sites, like in the middle of a desert like this, what you do is you can see the Milky Way in full glory. What you're seeing here is that you're looking from the sun in that direction, right? And you can see that the black stuff in the disk of the galaxy, that's dust that absorbs light. That's dust left over from the formation of stars. That's dust that's been there from which nothing has formed. And that's always there. Often it's associated with star formation. And that dust, this is the dust that you see. And here's the 4-meter telescope in Cerro Tololo, just to give you a sense of scale. And the other things you see in the sky, and these are 2 galaxies that you see with the naked eye, the Large Magellanic Cloud and the Small Magellanic Cloud. These are nearest tiny galaxies, just like the Earth has a moon. Our Milky Way has about 40 or so satellite galaxies that we know of. There are many more. The nearest ones, which were discovered hundreds of years ago, these 2 discovered by Magellan, for example, which is why they are named after him, you can see in the sky like little clouds. They don't go away. And then you realize that you're looking at galaxies. And this is our own galaxy, the Milky Way. And you can see why it's called the Milky Way, the legend of milk spilling from the breasts of the Roman goddess Hera as she went across the sky. I mean, in India, in various languages, we call it Akash Ganga, for example, which is the river in the sky. And this looks like a river, and all because what you're doing is you're looking at a band in the sky. Now, you can see that these are real pictures. The one that I showed you before is not a real, this is of course a real picture, but this is not a real picture. If you look at our own galaxy from inside, you look at it like this. But if you look at other galaxies that are like us, you can see that that's what galaxies look like. This is very similar to our own galaxy. So you can see that that's what our galaxy would look like if we were outside, and we would be somewhere here, right out there in one of the arms halfway across the size of the galaxy, right? And if you saw the same galaxy sideways, you can see that you can see the dust and the stars more linearly. That's another one, which is also, but you can see it completely sideways, right? And that's a real picture of another galaxy that is like our galaxy, but you can't see the spiral structure. You can see the dust lane in the middle. And this is exactly how we see our own galaxy, because we are not at the center. We are looking as if we are outside a town, looking towards the city center. And we're looking towards where the most of the stars are. We see through the dust in the galaxy. And this is what our galaxy really looks like, right? That's a real picture. That's a real picture taken by an all-sky camera of our own galaxy. This is taken from the Southern Hemisphere, again, from Chile, and a different observatory. But you can see that if you take a fisheye lens and take a picture of the entire sky, this is what our own galaxy looks like. And you can see it's very similar to this picture that we saw, right? So this kind of puts you in perspective of how our galaxy looks. Of course, we'll never be able to go out and see our own galaxy. And you can see that all the stars that you see in there, the stars in the sky are foreground stars beyond which you see the center of our own galaxy, and we are looking at it from outside. Okay? So that tells you the structure of our galaxy in a way. It's something we did not understand till the 1920s. In fact, this year we are celebrating the centenary of a famous debate that happened in Washington, D.C., and the National Academy of Sciences to discuss this very issue. How large is the universe? Is the whole universe what we call a galaxy? The word galaxy hadn't been coined yet. There were some people who thought that the entire universe is just full of stars and the universe is a stellar system. And then some people thought actually there are stellar systems that are island universes that fill the universe, which is what we believe now. But in 1920, this debate came to discuss all these issues and did not actually decide on what the structure of the universe is, but highlighted the whole issues of how large the universe could be. And the real answer came from measurements, which we'll talk about a little later. So in our local neighborhood then, where are we in the universe? We are the Milky Way galaxy, which has quite a lot of small dwarf galaxies around us. Here we've marked a few of them. Our nearest big galaxy, I showed you the picture of Andromeda with the moon, and the Andromeda Galaxy is M31, and that's 0.7 megaparsecs away. I told you the typical distance between galaxies is about a megaparsec, so 700,000 kiloparsecs away. And then it also has bunches of dwarf galaxies around them. We know of about 45 of them now, but there are some of them that are there. And together we call ourselves a group of galaxies called the local group. The local group consists of two big galaxies, some smaller ones, like, for example, the Pinwheel Galaxy M33, and dwarf galaxies surrounding us. That's our nice little local group. And the Andromeda Galaxy and the Milky Way are falling towards each other out of the expansion of the universe. It expanded with the universe, but then our gravity pulled each other back, and we are falling towards each other at about 120 kilometers per second right now, and we'll merge with each other in about 4 billion years, right? So you don't have to worry about it. That's not going to happen tomorrow. And in our local neighborhood, then, we can see simulations of galaxies. Is that we know that the nearest big cluster of galaxies is the Virgo cluster. I showed you a scale to it yesterday, and there are lots of filaments, filamentary structures of dark matter, and these little groups of galaxies are dotted on these. And on the large scale, that's what the universe looks like. The universe looks like a patch of filaments. We call it the cosmic web. It looks like a spider's web. And we are only recently, in the last 10, 20 years, learning about this, the fact that galaxies are not distributed in a nice, homogeneous, isotropic, three-dimensional, uniform distribution locally. Globally, in the whole universe, you can consider it to be homogeneous and isotropic, but in a very small volume, say a volume of 10 or 50 megaparsecs, you will find that the universe looks very stringy. And the web of strings are filaments that these are dark matter. This is a simulation of dark matter, and you can see these little groups of galaxies, and some of them have very concentrated galaxy groups, much bigger ones, which could be called clusters, right? And galaxies travel along these cosmic highways and go towards, gravitate towards groups, and then maybe towards clusters. That's what we believe now. And actually we see them this is, for example, on the left, actual observations of a three-dimensional, building a three-dimensional map of the universe. This is a slice through our local universe. Each point is a galaxy. This particular map has more than 1 million galaxies, and you can see how this kind of idea of the cosmic web, even taking a one-dimensional slice to the universe, shows us that it's like that. Now, going back to our own galaxy, let's look at before we leave this topic. I wanted you to look at how to do a small measurement in our own galaxy. So, for example, I told you that we live in this galaxy, and we are 8 kiloparsecs, or 25,000 light years away from the center, and these are the various arms. And what we are doing is we are going around the center of the galaxy like this in more or less a circular orbit. And we can measure these velocities and these distances. These have been done only in the last 50 years or so. Okay, so here we are. Here's a question, and I'd all like you to try and answer this question. So the question is, we would like to calculate how long it takes for the sun, along with the Earth and the solar system, to travel around the center of the galaxy once. I'm telling you that the sun is traveling at a speed of 220 kilometers per second, and that's its linear speed. And it has a circular orbit of radius 8 kiloparsecs. I'm giving you what a 1 kiloparsec is in meters. And I'd like all of you to try and estimate very fast how many times the sun has gone around the center of the Milky Way, spelled wrong, in its lifetime. Right? By the way, the lifetime of the sun is 4.5 billion years. I hadn't given you that. So in 4.5 billion years, how many times do you think the sun has gone around the center of the Milky Way? And here's a poll, and I'm going to start a poll right now, and I want you to, on your screens, press the answer that you think is right. Has it gone around less than 1 time? Has it gone around 5 times, 20 times, 100 times? Okay, and please, you have 20 seconds to press this. No, what's happening? Why can't I do the poll? Yes. So on your screen, you will see the 4 answers, and in real time, we're looking at how people are voting. I don't know why less than 1. Okay. A 100 people have already voted. I'll let this go a little. I'm urging you to take a guess if you haven't calculated, but you can do this calculation. Okay, 150 people have voted. So let me just end this poll. In this poll, it's very interesting that in the poll, the winner is less than 1 times the center of the galaxy, and 45% believe that it goes. We haven't really gone even once around the center of the galaxy. Less than 5, about 28%. 20 is 20%, and many people, almost 10%, believe that we've gone around almost 100 times. Okay, right. So let's get back to my calculation. So I told you that the sun is traveling at 220 kilometers per second at a radius of 8 kiloparsecs, and I normally, to do this calculation, you can do it very straightforward. It's 2 pi r, which is the circumference of the circle, divided by the time is the velocity. And so from that, you can find out what the time is, because I've given you the velocity and I've given you the radius, right? So, but the problem is that, you have to convert kiloparsecs and kilometers, etc. I'll give you a little trick to do calculations in astronomy, which you can do in your head without converting units. because you can use a system of units. And if you're doing stellar physics or galactic physics, you can choose your units. Just like in every subject, you can choose the most convenient units to give the numbers to be small. And in my calculations in cosmology, I always put g equals 1. And now g equals 1 means that there's always f equals gmm over r squared. G is always there. And if I put g equals 1, and I'm free to choose out of length, velocity, time, etc. I'm free to choose 2 other things to be my units. I choose my unit of distance to be a kiloparsec, because that's that's what typical galaxies are measured in. Typical velocities of stars and galaxies in the universe are measured in kilometers per second, and so I set those basic units. It turns out that if I put g equals 1, I put the unit of distance as a kiloparsec and a unit of velocity as a kilometer per second, my unit of time becomes very close to a gigayear, 10 to the power 9 years. That's very convenient. It's actually 0.97 times 10 to the 9 years. But in astronomy, that difference is okay. I mean, that approximation is okay. But the price I pay is that I have a very odd unit of mass, and that is 2.3 times 10 to the 5. I'm not using mass here. So just look at what we have to do here. We have to do is we take 2 pi r divided by v, and my v is 220 because my unit is kilometers per second. My r unit is kiloparsec, so it's just 8. So all I have to do is I have to say 2 pi r, which is 2 pi is about 3 times 8 is about 48, and divided by v, which is 220, right? And that gives you about 1/5 of a gigayear, and that's as I told you, 4.5 gigayears is the age of the sun, and that's about just a little less than 20 times the age of the sun, right? So what has happened is that the sun and the solar system has gone around the galaxy in its lifetime about 20 times the sun. Okay? So this is a very interesting and surprising result, because it just means that we have traveled the galaxy as the galaxy turns. The sun's velocity is more than the average, the large-scale turning of the galaxy, and the sun has gone and traveled amongst the stars so many times and seen a lot of different environments, and has sampled a lot of the life in the galaxy. Life meaning what's happening in the galaxy in its lifetime. It's absolutely amazing. And actually, this is just the component in the disk. It also goes up and down as it travels with a much longer time scale as well. And we have measured the perpendicular motion of the Earth in the galaxy as well. I would like you to also now, the rest of today, look at how an astronomer looks at the sky. And I said I would talk about the basics of observing the sky, because all this we need to put together in order to tell you how astronomers make measurements. So again, astronomers have this limitation that astronomers can't go and visit the subjects of their experiment, right? First of all, I can't perform the experiment. The experiment has already been performed for us. The universe is there. I can't say, okay, let's redo this experiment like you do in a physics lab or in a biology lab or chemistry lab. You can design an experiment which will be a way of observing the experiment that has already been performed, right? The Big Bang has happened and the galaxies and stars are already there. And the second limitation is I can't go and touch my objects or reorient them or insert a probe very close to the object and things like that. We can't do that. We haven't even gone to our nearest planet, let alone go to go outside the solar system and visit other galaxies and things like that. So we not only we can't measure distances very well, and we can only measure distances, angular distance in the sky, but we also have to make sure we understand how our information is collected. And so the information comes in form of gravitational, in form of electromagnetic radiation and now gravitational radiation from objects in the sky, and they are interacting amongst each other. We know with some basic laws of physics, which we assume are the same as our own laws of physics. There hasn't been any reason for us not to believe in that, right? So here we are, right in the middle. And so what we have to do is we have to define a system which orients ourselves in the sky, right? So you will hear these names over and over again in an astronomy course like this. So I thought I'd better define this so that it's the same for every one of you. I'm here on the Earth. Remember, I'm standing upright on the Earth and I'm looking up. So this is wherever I am on the Earth. I'm not on the top of the Earth, but as far as I'm concerned, I'm standing on top of the Earth, right? So here's a spherical Earth, and right above me is the zenith. And if you look at a plane that goes through the Earth, right, like this, that's called the horizon. That defines the horizon, right? So in three-dimensional geometry, we think in terms of great circles. If you have a sphere around us, actually this sphere does not exist. It's a virtual sphere. But think about it as a sphere around you, which is transparent, called the celestial sphere, right? Think about a sphere. Then if you have a plane that goes through the middle of the Earth, just under you, and cuts this sphere, it will be a great circle around you, right? A great circle is a circle that is a part of a plane that goes through the center of the spherical system, right? And it intersects the sphere in a great circle. The great circle will be called the horizon, and then the 90 degrees from that horizon will be your zenith, and right under you, it's the opposite of zenith, okay? So your zenith is your zenith, right? It won't be the same zenith for everybody else on the Earth. Now remember, there's always somebody on the other side of the Earth, southern hemisphere, who's pointing right down compared to you, and their zenith is your nadir, right? Okay, so this is why, for example, when you go to the southern hemisphere, the entire sky looks upside down, right? So, for example, if you see the Kalpurusha or Orion, the constellation with the shoulder and the head on top, Betelgeuse on top, and the sword dangling down, you go down to the southern hemisphere, you're looking at Orion, you'll see it upside down, right? And so this is not something that people think. I mean, you see cricketers thanking God, pointing up on the sky, here pointing their bat up. In Australia, they point the bat in that direction, right? So the sky is very different in the southern sky. And you can see already that from the northern hemisphere, half of the sky will be hidden from you. So here is the zenith and the horizon, and up and down are relative to you. Okay, so we have to keep this in mind when we travel the world looking at the sky. We observe in telescopes that are situated all around the world, and the sky that we see from different places is different. Even within India, the sky that you see from northern India is different slightly from the sky that you see in the southern India, because there's a huge difference in latitude. And then the sun, during the daytime, you know, that rises in the east and sets in the west, and it does not rise in the east every day. It rises due east only 2 days in the year. And during the year, you would find the sun move from its position in the vernal equinox, where it rises exactly at east, in the vernal equinox, March 21st or 20th, and then it moves north at its rising point and setting point every day, and it gets higher and higher up in the sky because of that, and then turns back at the day of the solstice, comes back, and then in the autumn equinox, it rises exactly again in east and sets in the west. And then it starts moving south, Dakshinayan, and then in December, this is the northern hemisphere, of course. In December, it rises the farthest away in the south from the eastern point, right? And this is why you see the sun the least in the sky on December 21. That's the shortest day. This is the length of the day, right? And the longest day of the year is the length of that day, right? The summer solstice in the middle of June. So we are now going in that direction. Now the days are lengthening, and after at the end of June, we'll come back and the days will get shortened, right? And likewise, if the days are long, then the nights are short. In the southern hemisphere, this is just the opposite. And you can see this from this diagram straight away. Okay. Now, the interesting thing is that the sun moves in a plane called the ecliptic, and I'll talk about this more later on. And so do the planets in the same plane, seen from us, right? In the same plane. And because the sun and the planets are in the same plane. And the plane that we see from the Earth looks like a line in the sky, as you can see, and that line is called the ecliptic. And the ecliptic crosses the equator at 2 places, and these are the places which are the equinoxes, which are the vernal and the autumnal equinoxes. And what we do is we measure the positions of the objects in the sky in latitude and longitude, just like geographers do, but our latitudes and longitudes are called right ascension and declination. For geographers, on the map, the longitude starts from a 0-degree longitude that goes through London, as you know, the Greenwich meridian. We've all learned this in school. And in astronomy, we take the point where the sun's plane, ecliptic, crosses the equator, the equatorial plane, the equator that goes through the Earth, and that place is called, that's where the sun is on 21st of March, the vernal equinox. That is the start of our longitude. From there, we measure the longitude and we call it the right ascension. That's the point, the vernal equinox, and you can see the plane going through the center of the Earth, and that's our zenith on top. And along the celestial equatorial plane, the plane that goes through the center of the Earth, we can measure in an anti-clockwise fashion an angle, and that gives you the right ascension, that is the longitude, and the latitude is exactly as we measure on the Earth, latitude from the equator upwards or downwards, and that's called the declination, right? And this is measured in degrees, and in astronomy we measure the right ascension in hours rather than degrees. 15 degrees make an hour, and 24 hours make 360 degrees. So, so you can see that what happens then is that these stars and constellations, if you look at the sky, they move around the north celestial pole, which is fixed. And if you're looking at it from the northern hemisphere, like here, and you can see that because the Earth is turning around the polar axis, that the whole sky will move around it as the night goes by. This is a very famous picture taken in the 1970s that completely set a certain tone. So many of us have taken this picture later on, but this was the first time this was done by David Malin. This was taken actually from the southern hemisphere, and a lot of times this picture is misused in various ways. This is nothing but a long exposure picture of the sky taken through the night. Okay, so you can, and so what has happened is that the camera is open and kept open all through the night, and all you're seeing is the stars going around. Okay, the Earth turns around the pole. In the case of the South Pole, there is no star in the middle. In the North Pole, there's Polaris in the middle. And you can see that all stars are going around. So you can also see this is probably a 10-hour exposure, or more than 8 hours, because that's the trail of a star as it goes around. okay? A lot of things have happened in the night. A car has gone and come out. For example, there's an astronomer on this telescope on this gangway who's smoking. You can see the cigarette moving, and also you can see the stars moving. So stars move. They move because the Earth moves. The Earth turns. And this is a typical night. And you can see that stars that are a certain angle above the horizon will never rise or set. They will go round and round and round. They're called circumpolar. And there are certain stars that will rise and certain stars will set, right, in the night. Okay, and that depends on where you are, depends on your latitude. The most interesting thing is this simple geometric exercise that is done in many books, and you can try it yourself, to show that this pole, the angle between the horizon and the pole, is the same as the latitude of your place. So I'm in Pune. My latitude is 18 degrees. So when I look at the night sky, Polaris will be 18 degrees above the horizon. And so stars will go around it all through the night, and stars that are less than 18 degrees away from Polaris will never rise or set. Okay? And this is a simple geometrical exercise that I'm not going to go through now, but you can see that if you look at your position, that's lambda, which is the latitude. If you are here on the Earth, that's your zenith. That's your horizon, which is perpendicular to the zenith. Okay? And if you're looking at any star in the sky, if you look at that angle, then you will see that and this is lambda, which is the latitude. Then it tells you that the position of Polaris, this is the direction of the North Pole, right? So this is where Polaris is, or the South Pole, or whatever, the polar axis around which the Earth turns, and so you can take a parallel to it at this point, and you can show that this angle between the horizon and the direction to the pole is the same as this angle, which is lambda. And so that is one way. For example, if you are kidnapped and somebody leaves you somewhere on the Earth and you don't know where you are, just looking at the stars, you can tell what latitude you are at, because you have to observe the night and see how the stars are turning, around which point the stars are turning. If you're in the northern hemisphere, you can see Polaris, and then you can measure the angular distance from the horizon upwards, and you know exactly where you are. So the last concept that I'm winding up on right now is this. You are an observer of the sky. What do you see if you observe the stars move around in the sky? You will see that the pole star, or the pole around which the night sky moves, is a certain angle above the horizon, right? Now, if it's the same as the latitude, then remember, if you're standing on the pole of the Earth, you're standing on the North Pole. I hope you understand that this pole, the latitude is 90 degrees, will be right above. It will be your zenith. So at the North Pole, the entire sky is circumpolar. No star sets and no star rises. The entire sky moves around. And so you see only half of the sky. You don't see the other half of the sky at all. If you are at the equator, this pole is right at the horizon. That means all star trails are semicircular, right? Every star sets and every star rises right at the equator. And in southern India, we are very close to the equator, right? But you can also see that if you are looking at this is your limiting circumpolar star. There will be all these stars that will never rise. You will not see. So this is why there's a whole bunch of southern stars, including, the center of our galaxy is actually, we can see it from southern India. It comes very, 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 a little bit above the horizon. But in order to study the center of our galaxy and where the most of the stars are, this is why we have to go to the southern hemisphere. And this is why I showed you the Milky Way so spectacular if you see it from the southern hemisphere, because we don't see it from the northern hemisphere as well. It will rise maybe up here, and you have to see it through a lot of murk. Okay, and so I hope you understand now that that the sky is not the same everywhere. The sky depends, the shape of the constellations and the patterns of the stars depends on where you are and on the Earth, and exactly which star you will see on a given day, and depends also where you are on the Earth. And this is why astronomers have to travel, not just because they have to go to high and dry places where their telescopes are, where the seeing is the best, and where there are fewer clouds and the air is stable, but also if they want to observe a certain object, they have to go to a place where they can see it in an optimal position in the sky and make measurements. Okay, so I'll stop here for today's lecture and look at the questions.
Thank you, Somak. So people who have asked questions, please raise your hands.
Let me, sorry, let me go to my participants list. Yes, so Asim, if you can go ahead and...
Yes, I will do it. So yeah. There was one question from someone who told me that his mic is not working, Sumed Kulkarni, so I'll just read out his question. Yeah. How do we decide that galaxies are older or younger?
Okay, so let me. I think in our galaxies course we will decide. We will look at all this. But what happens is that in galaxies we have a bunch of stars. Now stars come in all colors and shapes and sizes. Newborn stars are very hot, and because they are very hot, stars are black bodies. Their peak of their black bodies in the ultraviolet and blue. And so newborn stars are blue. As the star ages, it becomes like our star is a middle-aged star. It becomes yellow-green, and then towards the end of its life, its surface is very cold, and it turns into red and then goes into the near-infrared. So redder stars are older, younger stars are bluer. And so, and a galaxy is a mix of stars. And so when you look at a galaxy in general, and you look at a large number of blue stars and star formation is happening, younger stars, that helps you understand whether the galaxy is young. And older galaxies, like I said, elliptical galaxies, for example, have a lot more of the older stars, which are cooler stars, and so they're redder. You can also have red because of other reasons, but this is a general answer. Now, I think during the lectures on galaxies, you will get a much more detailed answer to this question. Anybody else?
Yes, so we have Sakshi Bhatia. I've unmuted you.
Sakshi, yes. Go ahead.
Sakshi, you have to unmute yourself and then just start speaking.
Sakshi, you can unmute.
Yeah, just 1 second. I'm not sure what is that. Yes. Okay.
I can't.
Go ahead, Sakshi.
Am I audible now?
Yes. Go ahead.
So my question is, if we know that in an expanding universe theory that the universe has expanding, so how can they gravitate into clusters?
Okay, good point. Again, I hope the rest of the course gives you an answer to this question, but I raised this issue, and that is as follows. The universe is expanding, and that means that the fabric of the universe is expanding. And that means the distance between the galaxies is increasing with time. And that's the length scale, the scale of the universe is expanding. But that doesn't say anything about gravity. Gravity is, the gravitation is a force that pulls, right? And so, so there's a tussle. For every galaxy, there's a tussle between the expansion of the universe that is taking it away from the nearest galaxies and the gravitational force of the galaxies that are pulling it towards them, right? So if you, and sometimes gravity wins and sometimes it doesn't. So if, for example, galaxies are very close to each other, F equals gmm over r squared, that force with a small r is big. And that can win. That is why I'm saying, for example, our nearest galaxy, the Andromeda Galaxy, is falling towards us. Why? Because the gravity, the force of gravitation between the two of us is much bigger than the force of gravity that will pull us apart, the force that will pull us apart because of the expansion of the universe. Similarly, that's what happens when a bunch of galaxies are close together. The gravitational force between each of them wins, and they fall together to become a cluster. Okay, right. Next question, please.
Next, we have Arjun Dawn. So I have unmuted you.
Arjun?
Hello, sir.
Yes.
So, sir, my question is about how do we come to know about the different arms of our own galaxy because we are looking sideways to it. So, how do we point out these arms of our own galaxy?
Very good point. So this is a very, very intricate subject, and this is the pictures look very simple, but they come from work that has been done over the last 100 years, and that comes from building a very detailed three-dimensional model of our galaxy by painstakingly measuring the distances to different stars and measuring their velocities and building a model out of it, right? So in the next 2 lectures, I'll be talking about how to measure distances to stars and galaxies. Yeah, and then you will figure out how this is done. And so you have to have a model, and you have information from many sources, not just the positions of the stars. There is cold gas in between the stars in a galaxy, and that cold gas emits the hydrogen emission line at 21 centimeters that the radio astronomers can detect. And through radio astronomy, we can find the 21 centimeter gas. That gives us, for example, an idea of the velocity field in our galaxy, how things are moving, and then combining the distances to the stars and knowing its position in the sky gives me a three-dimensional position, as well as the velocity field from within the galaxy. We can reconstruct this. And these things, the arms have been found, for example, and the various other components of the galaxy from this. I hope in the galaxies courses that we are in this, we covered this. Of course, we have 50 lectures and it's hard to cover everything in astronomy. But if you can pick up a basic book on galactic astronomy or even astrophysics textbook, you will find a lot more about mapping of the spiral arms of our galaxy. Okay.
I think a general request is to provide some such references. So maybe in one of the lectures, if there's a slide giving names of books, that might help a lot.
That would be very good. And also on our wiki page, etc., and website, we will put some references that you can look at.
Yes. Okay. So the next question is from Avik Kumar Basu. I have unmuted you.
Avik.
Yes. Good morning, sir.
Good morning.
Sir, my question is that Hubble Space Telescope is out there in the space above atmosphere. Then how come the seeing of that telescope is affected by the refractions or like that thing?
No, I didn't say that the seeing of the Hubble Space Telescope is affected. In fact, that's what I meant. I meant that we have to put telescopes on top of the atmosphere so that it's not affected by the seeing. It has other things limiting its resolution. It is, of course, a mirror, and so the mirror has its own diffraction limit, which we'll talk about later on. That limits it doesn't have infinite resolution. Any finite size mirror will have a limit due to diffraction. It has its the whole focusing regime, how well it can focus, and then its camera itself has a resolution element. It has a pixel, and that pixel would be small, but it does not suffer from any seeing. Thanks. Next.
Rahul Devarakonda, I've unmuted you.
Okay, good morning, sir.
Good morning. Yes,
so my question is, you showed us a picture of those patches of clusters of galaxies and stars. They look like a spider web.
Yeah.
Yeah. Now, why is it that the universe chose to form those patches and not a uniformly spaced stars? Why isn't it not uniformly spaced? Is it due to thermodynamic reasons, or is there something else?
I'm trying to think of how to answer your question in a sentence. This is, of course, the entire subject of cosmology and astrophysics. Large-scale structure, how structure formed, has been the topic of research from maybe the 50s, the 60s, and there are whole textbooks on it. It's very difficult to summarize in one sentence, but the whole point is that the universe, and also we don't understand now all the components of the universe very well. We understand that the universe is largely made of dark matter, and there is dark energy, and that in that baryons, which make up our galaxies and stars, are seeded, and they feel the gravitational influence of the dark matter, and the distribution of the dark matter is not the same everywhere, and baryons are seeded following the distribution of dark matter, and then they collapse into entities like galaxies and stars, etc. And then so these things form, and what we have now is that an observation that this is how the baryons are distributed, the stars are distributed, the galaxies are distributed. So in astronomy, our problem is reversed. We have a theory. We have many theories of how from the initial inhomogeneities of density in the universe, we formed the structure that we see now. But then what we have to do is to see the structure that we have in the universe now and make them match to these theories, and then infer what kind of matter, because we don't know how the universe started, what the initial conditions of the universe was. Nobody has written them down for us. And we don't even know what kind of dark matter underlies all this that provides the gravitational field in which all these things form. So the interesting thing in this game is that you have to proceed from both ways. You have to build your models. You have to then look at the observations and try to match them. And this is something that's going on now. And this is a very active research. If you come into the field and work in structure formation or cosmology now, these are the questions you are going to ask. Anybody?
I think we could just maybe take a look at the YouTube chat in case you find something interesting there. Otherwise, we can secure over time.
Actually, can I? Yeah, let's look at the hands here again. Right now I have a problem in accessing the.
Okay, I can read out a question or two from.
Can you do that, please? Yes.
Yeah. So Ritika Sethi asks, why do galaxies exist in spiral shapes?
Right. So that's a very good question. I hope that in the galaxies lectures this will be dealt with in detail. There are two parts of that shape that are very important. One is the disk part, the fact that it's flat. And actually what happens is that if you have a flat structure that is rotating, you will find such spiral patterns themselves emerging, and it's a flatness that's very important. I mean, you see the spiral patterns even when you swirl a cup of tea. But the interesting thing is that they're flat. And why are newborn galaxies flat? And that is because, for example, the galaxy is forming from maybe a spherical cloud or a three-dimensional cloud of gas and dust. And as they collapse, you will have certain axes that collapse faster than the others due to the basic inhomogeneity of the cloud itself. And as the collapse happens, one of the axes of the three axes of the three-dimensional structure will collapse faster than the others. And in the end, that will give rise to a spheroid that is more collapsed in one direction than the others. And this will happen because the thing is rotating, right? Because there's some angular momentum, and the angular momentum has a certain direction, and that determines that actually gives some preference along a certain direction about the others. If they were not rotating, then they would not have this preference. So you'll see normally these clouds collapse perpendicular to the axis of rotation. and as the cloud collapses, the speed also increases because the angular momentum is conserved. And so these things are flat and they're spinning. And as they're spinning, they produce things called density waves in the disk of the galaxy, which I'm not going to go into now, but somebody else will in the lecture on spiral galaxies, which produce these spiral arms. These spiral arms are transient in nature. They come and go. They are not permanent. And they are not very, very high perturbations, very dense perturbations in the density, but they stand out and you can see them. And these also, they are lined by these molecular clouds that form these newborn bright stars. So you can actually see them very prominently. Is there any other question that
we can take one last question? This is from Nisha NG, who has not raised her hand, but the question is nice, so I'll just read it out. Does the motion of the solar system around the galactic center have any prominent or notable effect on life on Earth?
This is a very, very good question. And this has been, of course, a very controversial topic also, but clearly it will have, right? Because as the solar system is moving through the galaxy, it's going through denser regions and it's going through rarer regions. And there is interesting thing is that it has a periodicity of motion perpendicular to the plane of the galaxy, which is of the order of a few tens of millions of years. And there has been suggestions, for example, that the dinosaurs were killed 65 million years ago, as you know, probably because of a volley of asteroids came and hit the Earth in the form of very giant meteorites and devastated the life on Earth. All the big life forms died. And this has happened several times on the Earth. And people think that it could be due to the fact that at that time the solar system has passed through either in its oscillation perpendicular to the galactic disk, or passed through regions where the tidal forces could have caused these things. We have periodic ice ages that people have tried to link to times when the sun would have passed through interesting parts of the galaxy. There has been very little research on this, given the fact that only now we are building a very detailed three-dimensional model of the universe. You will see in the next couple of lectures why it has been so difficult to do so. And once we have a very good three-dimensional model of the distribution of stars around us, I think we will know these answers much better. Thank you. I think we are coming to the end of our allocated time.
Yes, I think we won't take any more questions for this lecture.
I'm sorry I couldn't answer all the hands up. Write to us, and maybe in later lectures we can tackle some more of the other questions. I'll see you again at 10 o'clock tomorrow morning. Thank you. Bye.